So far we saw Fourier series and the properties of Fourier series. We saw some examples of them. Now let's solve some problems which involve Fourier series. Okay. The first question that we have here is that the Fourier series coefficient of some signal z of t is given. Okay. So it is given that z of t has some Fourier series coefficients ak. So we can express it like this. There is fundamental frequency omega, and it is given that we know this coefficient ak that corresponds to z of t. Now, the given question is, how do you find out the Fourier series coefficient of the even part of z of t? That is, let us call y of t to be the even part of z of t, and let it have some Fourier series coefficient, let us say bk k minus infinity to infinity e power jk omega t. Of course, the period will not change, so we can say that the fundamental period is still the same, and so the fundamental frequency also remains the same. So, only thing that changes is this Fourier series coefficient. Question is, what is bk in terms of ak? Can we find that in terms of ak? That's the question. Let's solve this now. So, what is the even part of z of t? The even part of z of t is z of t plus z of minus t divided by 2. Okay. So, then we can just plug in this expansion here. So, basically what is Fourier series expansion? It's a decomposition of z of t, right? So, you can expand it directly by substituting whatever we have here. It simply says that it is ak e power jk omega t plus the same thing, but now we have minus k omega t because of this minus t. Okay. So, now we have to somehow express this expansion in terms of the Fourier series coefficient. So, we need to just get some bk times e power j omega t. So, how do we get that? So, we can say that this is equal to minus infinity to infinity half ak plus something such that you have e power j omega t. Okay. So, e power j k omega t, the coefficient of that here is ak, so that comes in as such. So, what is the coefficient of e power j k omega t here? So, whenever k is negative, you get the exponent here to be j k omega t. So, the corresponding coefficient here is minus k. So, now what we can say that is, so this entire term equals bk. So, now we have an expression for the Fourier series coefficient of the even part in terms of the Fourier series coefficient of the original signal, and that is simply the even part of the original Fourier series coefficient itself. So, now we also learned earlier from the properties that when you have an even signal, then the Fourier series coefficients also turn out to be even. So, if you try to compute b minus k, it is also equal to exactly the same thing. So, b minus k is equal to bk. So, we get the exact property that we had studied earlier. So, now we have expressed the Fourier series coefficients of the even part of a signal in terms of its original Fourier series coefficients. Now, what if we had the odd part given to us? So, how do you compute the odd part? So, in this case, you just replace everything here and then say you have the odd and you have a negative term here. So, this term becomes minus and this becomes minus. So, this is the only difference, nothing else changes. So, for the odd signal, so this is for the even signal. So, for the odd signal, what do we have? We have bk to be equal to ak minus a minus k by 2, and the negative of the Fourier series coefficients here would now be just a of minus k minus ak by 2, which is equal to minus bk. once again we get the Fourier series coefficients to be odd. So this satisfies the properties that we already had seen. So this is a nice reinforcement that the properties that we studied are also correct. Okay, so we now found out the Fourier series coefficient of both even and odd part of the signal in terms of the Fourier series coefficients of the original signal. Now using this, can we find out the Fourier series coefficients of sine omega t, cos omega t from the Fourier series coefficient of e power j omega t? So what is the Fourier series coefficient of e power j omega t? That's the first question that. So if z of t is equal to e power j omega t, and you want to express this in terms of ak e power j k omega t, then just by looking at it and comparing coefficients, you can directly say that ak is equal to 1 for k is equal to 1 and 0 elsewhere. So just by comparing coefficients, you can directly say this. So the Fourier series coefficient of e power j omega t is very easy to compute, because all we need to do is just compare coefficients and we are done. Now, so if this is easier, then the computation of the Fourier series coefficient of cos omega t and sin omega t should also be easier. Why is that? Because cos omega t is nothing but the even part of e power j omega t. So because this is the even part, now what is the Fourier series coefficient of cos omega t? So let's say bk is the Fourier series coefficient. Then we can say that bk is equal to ak plus a minus k by 2. Okay. So from this expression, what happens when k is equal to 0? When k is equal to 0, we have a0 plus a0 by 2, but we know that a0 is already 0, which means b0 is 0. What happens when k is equal to 2? When k is equal to 2, we have a2 plus a minus 2 by 2, which is also 0, so on. So what happens when k is equal to 1? When k is equal to 1, we have a1 plus a minus 1 by 2. Okay. Now we know that a minus 1 is 0 from this relationship. So the only thing that we have here is a1 by 2. And what is a1? a1 is 1. So b1 is 1 by 2. What about b minus 1? b of minus 1 is a minus 1 plus a of 1 by 2. A minus 1 is once again 0. a1 is 1. So b minus 1 is 1 by 2. For all other values of k, this is 0, which means we have this to be equal to half when k is equal to 1 or minus 1, 0 otherwise. This is the Fourier series coefficients of cos omega t, again, which makes sense, because if you expand this in terms of the Fourier series coefficient, what do we have? So we have cos omega t to be equal to bk e power j k omega t, and substituting this bk value, we just get cos omega t to be equal to half for k is equal to minus 1, so e power j k, and another half for k is equal to plus 1. This is exactly the expansion of cos omega t, right, in terms of e power j omega t. So we get this back. Of course, this is for k equal to 1. So we can do a similar thing for sin omega t as well. So sin omega t is equal to the odd part of e power j omega t divided by j. Alright. So which means what we need to do is just first compute the coefficients of the odd part. And what is the coefficient of the odd part from this relationship? We can find that out. So from this relationship, we can say that bk is equal to ak minus a minus k by 2. Once again, due to the same explanation that we gave before. So this is equal to half when k is equal to 1. Okay, just substitute k is equal to 1, you get a1 minus a minus 1, a minus 1 is 0, so you just get half. And when k is equal to minus 1, you get a minus 1, which is 0, minus of a minus 1. So a minus 1 is 1, so minus of a minus 1 is minus 1 by 2 and 0 elsewhere. Okay. So this is the relationship that we get for sine omega. So what is the coefficient now? The coefficient is now bk by j. So remember there is a j here. Okay. Bk divided by j e power j k omega t. In other words, if you expand this sine omega t in terms of these coefficients that we have here, we get that sine omega t is in fact equal to, when k is equal to 1, you get e power j k omega t divided by 2j, and when k is equal to minus 1, you get minus j k omega t divided by 2j, which is exactly the expansion for sine omega t that we already know. Let's try now something quite different. So the question here is, find the Fourier series of the periodic rectangular pulse, but not directly, but by using the Fourier series of the impulse train. So how do you use this? So this is where we use a lot of properties that we learned about Fourier series and then use them here to find out the Fourier series of the periodic rectangular pulse from the Fourier series of the impulse train. So what is the Fourier series of the impulse train? So what is the impulse train first? So let us say the impulse train is some z of t. We represent that as n equals minus infinity to infinity del of t minus nt. So this is our impulse train. Okay. And what is the Fourier series coefficient of the impulse train? This is simply nothing but ak e power j k omega t. And remember, this ak is 1 by t. So this is something which we already saw. So this is the Fourier series representation of the impulse train. So how does the impulse train look like? The impulse train simply looks like just a period of impulses. Okay. So this is 1, when it is 0, and then t minus 2t, and so on. This is the impulse train. Now the question is, let's say we are given the periodic rectangular signal. We are supposed to find its Fourier series representation. Let's say that we are supposed to find some ak e power jk omega t. We are supposed to find this. So how does the rectangular signal look like, a periodic rectangular signal? So we know that it looks like this: 0 minus t by 4 plus t by 4. This is minus t, this is plus t, this is at 3t by 4, and this is minus 3t by 4, and this is 5t by 4, okay, and so on. Now what if you take the derivative of this? That is, you take the derivative of, and if you plot this, what would you get? So this is y of t. Plot the derivative. So if you plot the derivative, how does it look like? So this is a straight line. So in all those places, you will just get zeros. But there is a sharp increase here. So remember, what is the derivative whenever there is a sharp increase? You get an impulse. This is an impulse at minus t by 4. And this is an impulse at plus 3t by 4, and there is another impulse at minus 5t by 4, and so on. Similarly, for the falling edge, we have another impulse. Okay, so this is at t by 4 and 5t by 4 and minus 3t by 4. Now, can we somehow connect these two signals? Okay. So we have z of t here and we have the derivative of y of t here. Now if you notice here, this gap is still t, okay, and similarly this gap here is t. So what we can say here is we can consider all the positive impulses and let's call that as some x1 of t. Let's call all the negative impulses as x2 of t. So clearly the period of both x1 of t and x2 of t is capital T. So if the time between any two impulse in these is exactly capital T, which means x1 of t is an impulse train, but the impulse train here actually has an impulse at 0, but we don't have an impulse at 0 because it is shifted now. So in other words, x1 of t is nothing but z of t, but shifted to the left by t by 4. So what is shifting to the left? It is adding a positive value, which is plus t by 4. Now what is x2 of t? x2 of t is negative of the impulse, but then it is not having an impulse at 0. It is shifted to the right. So we have shift of t by 4 to the right. So now what we have done here is we have expressed the derivative of the rectangular pulse in terms of the impulse train. So we have here z of t plus t by 4 minus z of t minus t by 4. What is the Fourier series coefficient of some signal which is shifted by some time? So this is where we use the property that we studied before. Whenever there is a time shift, what happens? So z of t minus some s, what is the Fourier series coefficients of that? The Fourier series coefficients of that is the same thing, but multiplied with e power minus j k omega s into e power j k omega t. Okay. So by this relationship, we can say that z of t minus t by 4 has Fourier series coefficients which is 1 by t e power minus j k omega capital T by 4. Okay. So this is our Fourier series coefficient, and z of t plus t by 4 will have a Fourier series coefficient which is given by 1 by t e power plus j k omega t by 4 e power j k omega t, which means the Fourier series coefficients of the derivative now is nothing but summation 1 by t, the Fourier series coefficient of these things, which is e power j k omega t by 4 minus the Fourier series coefficient of e power j k omega t by 4, that is minus the Fourier series coefficients of z of t minus t by 4, which is what we have here, times e power j omega t. Alright, so what is this? This is 1 by t sine k omega t by 4 times 2j. Now how to get the Fourier series coefficients of y of t? So once again we use the property that whatever that we have studied before, that if the Fourier series coefficients of a signal z of t is known, then the Fourier series coefficients of its derivative can be directly given by just multiplying j omega k. In other words, we know that ak times j omega k is equal to whatever we have here, that is 1 by t sine k omega t by 4 into 2j. So this is the Fourier series coefficients that we have here for the derivative of y of t, and this is the Fourier series coefficient of y of t. And we know that the relationship between the Fourier series coefficient of y of t and its derivative is simply the Fourier series coefficient multiplied with j omega k. This is the property that we have seen before. So, these coefficients should be equal to this coefficient. So, that is the equation that we are doing here. So, now substitute omega as 2 pi by t. Okay, substituting omega as 2 pi by t, and just get 2 pi. So, this tells us that ak is equal to sine k pi by 2 divided by k pi. So, this was the Fourier series coefficient that we derived for the rectangular pulse even earlier, remember. But now what we did not do this integration at all. All we did was we repeatedly kept applying some of the properties. So, this is a nice example where we saw the property of the Fourier series coefficient relationship between the signal and its derivative and its time shifted values. So, just by using these two properties and knowing that the Fourier series coefficients of an impulse train is just a constant, we were able to find out the Fourier series coefficient for rectangular pulse by putting all the properties together. Alright, so now this is another interesting example. This is a very practically relevant example. So, what is given here is an ideal low pass filter. So, it says that an ideal low pass filter has a cutoff at 120 pi radians per second, which is 60 hertz in frequency. So, what does this mean? So, we are considering a system which has some input, let us call some z of t, and the output is some y of t, and this is an ideal low pass filter. So, the frequency response of the ideal low pass filter, so this is the frequency response, is nothing but a rectangular function, and here we say that at 120 pi it stops having a non-zero value. After that it is all 0, until that it is 1. Okay. So, this is an ideal low pass filter. So, this is the frequency response of the ideal low pass filter. Now, given that this is an ideal low pass filter which has a cutoff at 120 pi radians per second, the question is, find out what will be the percentage of input power to the output power when the input is a unit rectangular wave of period 20 millisecond. Okay. So, given that t is equal to 20 milliseconds, what is the fundamental frequency? It is 2 pi by t, which is 2 pi by 20 into 10 power 3, which is nothing but 100 radians per second. Okay. Now, we just saw how to find out the Fourier series coefficients of the unit rectangular pulse. What is the Fourier series coefficient of the unit rectangular pulse? So, let us say the rectangular pulse is z of t, then we have k equals minus infinity to infinity sine k pi by 2 divided by k pi. So, this is from the previous problems and examples that we have solved earlier, e power j k omega t. So, this is the Fourier series coefficients of the input. What is the Fourier series coefficient of the output? We know that it is, once again we use whatever we studied before, we will say that it is the Fourier series coefficient of whatever was the input multiplied with the frequency response, right, that is it. And what do we have here? The frequency response simply says that omega, whenever it is less than 120 pi, you have 1, 0 otherwise. So, when k is equal to 0, what do we have? When k is equal to 0, this term is half. So, we have lambda to be equal to 1. So, we have half plus, when k is equal to 1, what do we have? When k is equal to 1, this term is 1 by pi. This term is lambda of 100 pi. So, 100, for lambda of 100 pi, we still have 1, which means you have e power j omega t. For k is equal to 2, this term is anyway 0. Okay. For k is equal to 3, we have minus 1 by 3 pi. but this term is 300 pi, lambda of 300 pi here is 0. So, which means what do we have here? We have 0 from all other values of k here. So, this is for the positive values of k, 0 and positive values of k. What about the negative values of k? So, for k is equal to minus 1, then we have plus once again 1 by pi. So, when k is equal to minus 1, you have sine of minus pi by 2 by minus pi, which is 1 by pi, minus minus anyway gets cancelled. So, lambda of minus 100 pi. So, here from this frequency response we can say that for minus 100 pi also the eigenvalue is 1. That is the ideal low pass filter. So, you have 1 here. So, we get e power minus j omega t. Once again for all other values of k you get 0. So, the output consists of only these 3 terms and nothing more. So, what has the low pass filter done? The low pass filter has effectively removed all the high frequencies and left with only this DC. This is 0 radians per second, and this one has 100 pi radian per second, and this has 100 pi radians per second. All other frequencies have been effectively removed at the output. So, this is what we see as a low pass filter's function, and it has performed correctly very well. Now, the question is, what percentage of input power is present at the output? So, what is input's power first of all? So, this is a periodic signal, which means all we have to do to find out the power is to simply find out the energy in one period. So, in this case we can simply integrate the energy in one period. So, the energy in one period is minus t by 2 to plus t by 2. So, this is a rectangular pulse, because of which it is 1 between minus t by 4 to plus t by 4, which means you just compute 1, which is nothing but 1 by t times t by 4 plus t by 4, which is just half. So, the power of the rectangular wave is half. Now, what is the power at the output? Now, to directly integrate this is going to be tedious, but what we can do is we can use Parseval's theorem. So, what does Parseval's theorem say? That if you want to find out the power of any signal, you do not have to compute the power in time domain, you can just look at the frequency domain, okay. That is the Fourier series coefficients. Simply square the Fourier series coefficients and you are done, okay. So, now what is the power? The power is 1 by 4 plus 1 by pi square plus 1 by pi square, okay. In other words, this is 2 times pi square. So, what have we effectively found out here? So, we have found out the output power. So, the input has a power of half. Of that, the DC value at the output takes 50%. So, how much is 1/4, right? So, 50% of the input's power is actually present in the frequency, which is omega equal to 0, okay. And at omega equal to 100 pi, the remaining power is present. So, what is this remaining power? So, this is 2 divided by pi square, which is you can say roughly about 0.2, okay. So, this is roughly 0.25 plus roughly 0.2. So, the amount of input power that is actually present in the output is now given by which is roughly about in this case, it so turns out that the 90% of the input power is present in just the first two components of the frequency concerned. So, it is present in the DC, the 50% of the input power is present in the DC itself, and the remaining is present in its first fundamental frequency, and only 10% are present in the harmonics in this particular case. So, you can do an analysis of how much power of the input is actually present in what particular frequency by such an analysis using Fourier series coefficients. Another thing, if you notice here, in order to compute the power of the rectangular wave, we used the time domain definition, but for the output we used the Fourier series definition by Parseval's theorem. So, many times it happens that the computation of power in time domain might be easier in certain cases. There you use this integral directly, or in other cases we directly use the Parseval's theorem and Fourier series representation, because computation of power there might be easier. So, whichever turns out to be easier, we pick that and then try and compute the power using that particular expression.